The first question would be, what is climate data? So to understand what climate data is, we first have to understand what climate is. By definition, the average course of condition of the weather at a place, usually over a period of 30 years, according to World Meteorological Organization or WMO, is called climate. Just imagine that you're walking on the beach along the coast and you're with your dog and you choose a kind of pathway or a trend or direction and you walk along this direction. So that would show the direction that you're heading to. But your dog is gonna move around randomly around your trend because you're kind of controlling the movement of your dog, so he cannot go far away from your trend. So this trend, this direction, this pathway over a larger time is called climate. And the fluctuations around this trend is called weather. So the weather has kind of time scales of 1 day to 1 week, and the climate usually is considered within 30 years. On the other hand, according to Merriam-Webster, data is defined as factual information like measurements or the statistics that we gather, which is used also as a basis for reasoning, discussion, or calculation. So to understand the climate, we have to gather information and the statistics from the climate. But our ultimate goal to understand the climate is the response of the climate system to increasing greenhouse gas concentrations. So we want to know what's going to happen with our climate system in the future as we burn more fossil fuels and as we humans are changing our environment. So what's going to happen? That's the most important question. So before that, we have to understand our climate system. What is the climate system? So usually the scientists define climate system by 5 components: the atmosphere, all the gas around us in the climate system; the hydrosphere, which is all the water inside the climate system, oceans, seas, lakes, and the rivers; and cryosphere, ice, all the ice within the climate system, like the glaciers, like the sea ice, like ice sheets, or for example over Greenland; and the lithosphere, Earth's upper rocky layer, like mountains; and the biosphere, all the living things within the climate system. The humans are also part of biosphere, and the most dangerous part of the biosphere. And the trees and the grass, whatever lives, and the animals. And all these components have a kind of coupling or interaction with each other, which means, for example, changes in the atmosphere, changes in the biosphere, gonna have a kind of effect on the atmosphere, and the atmosphere has a kind of feedback on the ocean. But all these components are gonna change in different time scales. For example, the atmosphere is changing very fast, but the ocean is changing very slowly, like at time scales of like 10 years or for the surface layer of the ocean. But for deeper ocean, for example, the circulation within the ocean, we have time scales of 100 years to several thousand years. Or the soil is changing much slower than the atmosphere. And all these has a kind of feedback on each other, which means if we change the atmospheric concentration of greenhouse gas concentrations, then we're gonna change the temperatures in the atmosphere, and that's gonna have feedback on, for example, on the ice and the ice is gonna have feedback on the ocean, and the ocean circulation gonna change the atmosphere again. So there's kind of feedbacks exist in the climate system, which makes it very complex to study because of all these complex feedbacks in the climate system. So to understand this complex climate system, we started to gather information. Yeah, in order to understand this complex climate system, we started to gather information of it. So nowadays, we are gathering information from the ocean surface and from deep ocean, from the atmosphere in different layers, from satellite, from the aircrafts, from the balloons, from the radars, from the lidars, over the surface we have the automated observation stations, and all this information would be gathered in a center and later on would be fed in our knowledge of the climate system and in our, for example, weather forecasting system. Now what we know about the climate system. By gathering the information from the climate system, we know that the temperature is rising after the Industrial Revolution, and it's rising at a rapid pace. And we know that the sea ice is also melting, and the sea level is also rising. So we know these things based on our data that we have collected. And we know that the temperature is rising globally with some kind of exceptions. For example, here we call it kind of warming hole in North Atlantic, because there is a hypothesis that says that the ocean circulation is slowing down, and that would have a kind of feedback on heat transport in North Atlantic. And on the other hand, that would also have a kind of feedback on the atmospheric precipitation. You see, for example, in Central Asia, there are some parts of the Central Asia and Middle East and even monsoon area that are receiving less precipitation, and some parts more precipitation. But the combination of these two, temperature and precipitation, which is shown in this dry index, it's called the Palmer Drought Severity Index. It's based on precipitation and the temperature both. So because the increasing temperatures is going to increase the evaporation. And although the precipitation is increasing, you see that the combination of the two is leading to more dry conditions since 1980 in Central Asia, for example, in large part of the Central Asia. And we know that lots of lakes are starting to dry out in Central Asia, which never happened before. So the other question would be, we know that the climate system has different time scales. They are changing, the component of the climate system is changing at different pace. So is this 100 years of data enough to understand the climate system? Probably no. So what should we do then? Yeah, there is an opportunity to go back in time with the help of the so-called proxy reconstructions. We know that some components of the climate system is kind of reacting or saving information of the climate change. For example, if you look at the tree rings, a tree needs energy and moisture to grow, to produce a ring per year. Energy means, well, temperature, and moisture means, for example, precipitation. So these two factors are gonna control the growth of the tree ring. So based on this information, we could somehow reconstruct the climate in the past, or using the sediments, using the ice cores, or using the pollen data or the historical records we can reconstruct the climate of the past. In this case, we call it paleoclimate study. So based on them, you can see that during the last millennium, the temperature was fluctuating around some mean, and the cooling trend was not that high. But after the Industrial Revolution, we see a kind of rapid increasing in the Northern Hemisphere temperature. So we call this plot the so-called hockey stick. And we know again from the proxy data that if you look at the last 1 million years, we had different warming and cooling periods or cycles in our climate system. These warming periods are called the so-called interglacials because they were between two ice ages. Here you can see the carbon dioxide during the concentration during the last million years. The interesting thing in this plot is that we never have been exceeding this limit before in 1 million years. And the other interesting thing is we are increasing the carbon dioxide concentration in the atmosphere at the pace that never have been before in natural variability of the climate system, which means we are increasing the carbon dioxide concentration like 1 million times faster than the natural variability. So coming back to our main concern, what's going to happen in the future if we increase our carbon dioxide concentration in the atmosphere? For that, the most sophisticated tool that we can use based on the knowledge that we have gathered of the climate system, for example, from our observation, we have now some equations governing the climate system, and we use them and we solve them computationally using the numerical simulation system called general circulation models. So the general circulation model tried to solve all these couplings of the component of the climate system, and they use they divide the globe into different boxes that they solve the equations on. They are called the so-called grid cells, and these boxes can go in different layers of the atmosphere and in deeper in different layers of the ocean. And if we increase the number of these boxes, then we are able to have more detailed information about the climate system. But the problem is, as we increase the number of the boxes, or as we increase the resolution of the model, on the other hand, we need more computational power. So there is a kind of trade-off between the complexity and the detailed information that we could get from the general circulation models. If you look in the evolution of climate models in time, in the 1970s, these models were very simple. They were getting just the atmospheric part of the climate system. And in 80s, we added land surface phenomena into the climate system. And now in 2020, we have a lot of information that we could simulate in the climate system in a GCM, and with a higher resolution because our computational power is increasing with time. And usually we use a kind of ensemble of climate simulations instead of just running one simulation for the future, which means we are more democratic in weather forecasting. So if we have more than one climate simulation, we can decide better how the climate will look like if we have like 40 or 50 climate simulations and 30 of the 40s tell us that the Arctic is warming up, so we could decide better than if we can add some kind of certainty into our decision if we're going more to which direction, warming or cooling. So that's the kind of basis of also the weather prediction. So what is the difference between the weather prediction and the climate projection? Usually we use the climate and we evaluate the climate models based on the present data and the past data that we have to see if the model was able to capture the changes in the past. But the weather prediction models usually start from 1 week, 1 month, and go to 10 years, where we have the decadal prediction. And that's the limit of our prediction. Because as we go further in time, our uncertainty will increase. And we have different problems to deal with. For example, if you look at the weather prediction models, we try to predict 1 day or 1 week in advance. And our problem is kind of related to the so-called initial value problem. So if we know the starting point of the simulation better based on more the observed data, then we can have a better simulation or the forecast. There is a so-called memory in the atmosphere. So if we have, for example, today in Berlin, 15 degrees Celsius, so tomorrow the temperature of Berlin will never be minus 40. So we know that the atmosphere is gonna kind of change around some initial condition. But as we go further in time, if you look at the forecast for 1 week, probably the certainty will decrease. And if we go further in time to the time scales of the centuries, then we can forget about the initial conditions. And our problem would be the boundary value problems, which means what are the external factors? If we want to, let's say, forecast or predict 100 years in advance, the problem is we never know how many volcanic eruptions we're gonna have in 100 years. We don't know how is the carbon dioxide emission in 100 years. We don't know how the humans are gonna behave in the future, because it's very, very dependent on our behavior. And for the decadal prediction, you're somewhere in between. So you have more problems if you want to predict 10 years in advance. You have problem of boundary values and the problem of initial values. Usually for climate forecasts, as I said, you have a kind of ensemble of climate simulations. And very small variations of initial condition will lead you to different climates as you run the simulation for 10 years. But on the other hand, for climate projections, usually what's going to influence these simulations are the boundary conditions. And what we do usually is the scientists, the social economists have decided to describe the so-called representative concentration pathways for the future scenarios of CO2, for example, concentration in the atmosphere. So they decided, for example, we might have a kind of green pathway, or our goal might be to just reach global temperature warming below 2 degrees Celsius, then we have to start to reduce our CO2 concentration in year 2030 to stabilize the warming. Another scenario is the RCP 4.5, which says that, okay, we might delay our decrease of CO2 concentration up to year 2070, and then we start to stabilize it. And the most aggressive RCP would be business as usual. We're gonna burn fossil fuels as we have done during the last 200 years. And we reach somewhere that we never know where. So we use these RCPs and we fit our GCMs or general circulation models with this information. And we are interested to see how the model simulations will react based on these pathways that we declared. But before doing that, we should evaluate our GCMs if they are useful. So this plot is from the first assessment report of the Intergovernmental Panel of Climate Change, or IPCC, from year 2000. So at that time, our models were like 20 years or older than today, and they were not so complex as today's model, with coarser resolution, of course, around the globe. But what is interesting is the red line is showing the observation of the temperature changes, and the black line is the ensemble mean. What you can see is that there is a very nice correlation between these two lines, and the models were able, the ensemble mean was able to predict the trend of the warming, with some exceptions. For example, here, or year 2008, 9, or at year 2000, and these overestimations are coming from volcanic eruptions. There were no way that these model simulations could predict the volcanic eruptions, because humans cannot predict the volcanic eruptions. So with that, now we want to see how the models will react to different RCPs, or the pathways, or different pathways that the human gonna increase the CO2 concentrations. And I show you an example of that from a GCM model. Now we are interested to see how the climate will react to the changes in greenhouse gas concentration, following the 3 different scenarios, or the representative concentration pathways, RCP. As an example, we choose Max Planck Institute Earth System model and look at the output of the model. We select 2 different variables, near surface temperature and the precipitation. For that, we can use a very nice example of model visualization. Go to this address here, you can see that. It's a tool conducted by German Climate Computing Center, DKRZ, and the AdaptViz, which is a startup here in Germany doing scientific mapping. And from this tool, you can choose, for example, mean temperature change over time. From, if you want to have all the 3 RCPs that they present here, you can choose all the 3 RCPs. On the left panel, you have the RCP 2.6, RCP 4.5, RCP 8.5. And if you want to have more information about it, you just click on the info button. Then you have the information about the RCPs, different RCPs. For example, RCP 2.6 is the 2-degree target. RCP 4.5, delayed climate protection, and the last one, which is business as usual. Now we can go start our visualization from year 96. Here on the left side you can see, and the temperature anomaly to the period reference period of 1986 to 2005. So the difference between this year and each year. So it shows how much this year was warmer or colder than the reference climate time slice. So I start the visualization. You see, from 2002-3, the the Arctic region is starting to warm up in all of the three scenarios. And if we zoom in our region here, Central Asia, you see in 2030s the climate is getting ready up to between 1 and 2 degrees Celsius warmer than the reference climate. And in RCP 8.5, business as usual, it's more pronounced, and even we reach warming of more than 4 degrees in a business as usual scenario. So that's a kind of example of very nice visualization. You can zoom in, zoom back, look at different parts of the globe. That would be the response of the climate system to the selection of pathways that we choose for emitting our greenhouse gases. You can also look at other variables. For example, let's select just one scenario, for example, RCP 8.5. I can also open another window, so then we can somehow compare the two variables, for example, temperature and the precipitation, side by side. So I also try to have these the country lines. Here you can click on line, first for English, and line, country borders. I zoom again in a region. I choose the change in precipitation over time, for example, for the summer times. And I go to year, let's say 2000, stop. Go back to year 2000. So I will start both of the simulations. More or less they are showing the differences. Oh well, that should be, sorry, RCP 8.5, because the left one is RCP 8.5. So I start it again. You see how they are changing as the climate gets warmer. Also we have in RCP 8.5 in summer we have also less precipitation, so the warmer area and less precipitation in our region probably gonna lead into drought events, which we have also observed in the observation data. So that's these are some kind of tools that we can use for visualization if we are not an expert. Or as you can see, at the end of the century, we reach like 4 or 5 degrees Celsius warming, but that's for the summer. But if you look at winter, there are some parts of Central Asia which receive more precipitation, but the problem is when it gets warmer, on the other hand, If you have this warming, let's say I go to 95, here 95. Well, here you have 90. Come back. Yeah. When you have this extreme warming, so this increase in precipitation would also be cancelled out by evaporation. And the system is gonna be drier. Yeah, the problem is with warming climates, this increase in precipitation would also be cancelled out by evaporation. So when you have like 5-degree increase in the near surface temperature, which means the temperature at 2-meter height from the surface. So the surface might be even more warmer than the atmosphere. And that leads to more evaporation, and the soil gonna be more dry, and that will lead also to dry conditions. So it's a kind of positive feedback in the climate system. So if we rely on our knowledge of climate system, and if our knowledge of the climate system would tell us that our future, due to our greenhouse gas scenario, would look like that, so that might be a very serious problem for us, especially in Central Asia, where the population is very tuned to very small variation of the precipitation, or where the water is scarce. And here there are some more examples of visualization tools that you can check it out by yourself. So in summary, climate models have their uncertainties, which means principally they are all wrong, but they can give a kind of picture or feeling what's going to happen in the future. We cannot predict the future like in 100 years in advance, but we can project it. We can see, based on different pathways that we choose, how the climate is going to react to these pathways. And as the time goes on, our computers are going to be more powerful, then we can have more complex simulations which have more, for example, resolutions, or they can capture more details of the climate system. And we can make larger ensembles with different model simulation. And with that, we can increase the certainty in our decisions about the future of the climate system.